This meeting is being recorded.
Very good afternoon, all of you. Am I audible? Am I audible? Okay. Okay. So very good afternoon. Screen is visible.
Yes, sir.
Okay. Now, in last lecture, what we have discussed? We have discussed about the accumulation mode, right? Then inversion mode and depletion mode. Okay. These three are the basic working modes of MOS transistor. Now, next point is MOSFET design equations. Okay. So see, any semiconductor device, you take an example of a BJT or any even a power electronic device, SCR, right? Triac, diac. So every semiconductor device has its current and voltage equation, right? So similarly, MOSFET also have MOSFET also has its own design equations, IDS and VDS, right? So consider the diagram. So first, this terminal is the gate, this is the drain, and this is the source. So here you are applying gate to source voltage. Basically, this terminal we connect to the ground, and here drain to source voltage, right? So this is the diagram. Now this length of the channel is nothing but L. This is the depletion layer formed because of the different what we can say voltage applied to the MOS. So these are the some what we can say uh, assumptions. Before starting with the derivation of the design equation, okay, first you have to make these three assumptions. What are these three assumptions? Dr is equal to minus dx upon mu w q1 of x. Okay, what is D stands for? Derivation, right? Derivation of R, that is total resistance, is equal to this X, derivation of the X divided by with respect to mu W Q1 of X. Okay, then dV, derivation of V is equal to IDS into derivation of dr. Now, what is this Q1 of X? Q1 of X is equal to minus VGS minus V of X minus VT. That means threshold voltage multiplied by Cox. What is this Cox? It is a Cox is nothing but the MOS capacitance, right? It's a MOS capacitance. Now consider this as equation 1. Consider this as equation 2. Consider this as equation 3. Okay. So by substituting equation 1, this equation into this equation, you will get IDS limit to 0 to L, dx is equal to, we have to put this dr value into this equation. So minus IDS into dx upon mu WQ2. What is this W? Width of the channel. And what is this L? Length of the channel. And this is the width of the channel. W stands for width of the channel. So you will get this equation. Now again replacing this Q1 or equation 3, right? It's Q1 X value in this equation. You will get IDS is equal to mu W by L Cox integration 0 to VDS in bracket VGS minus VT minus VX into dV, right? And finally, after solving this equation, you are getting IDS is equal to mu W by L Cox in bracket VGS minus VT into VDS minus 1 by 2 VDS square. Okay, you have to solve this integration, you will get this equation. Next, now when this VDS is equal to VG minus VTX, right? When this VDS is equal to VGS minus VT, the NMOS is operated in a saturation region and we obtain IDS is equal to 1 by 2 mu W by L Cox in bracket VGS minus VT bracket square. Okay, and this is the final, or you can say one of the equation of IDS, drain to source current. Okay, and if you consider the now the channel length modulation phenomena, now this L dash will be L minus delta of L. So now again if you replace this in this above equation, you will get IDS is equal to 1 by 2 mu. Now what is mu? Can anyone? What is mu? Mu is the mobility of electrons. Okay, mu is the electrons mobility, W is the width of the channel, L is the length of the channel, Cox is nothing but gate capacitance or MOS capacitance, VGS is nothing but the gate to source voltage, and VT is nothing but the threshold voltage. Okay, so you must have to clear with all this phenomenon. Now after considering this channel length modulation phenomena, the corrected saturation current becomes IDS is equal to 1 by 2 mu W upon L dash, where L dash is equal to L minus delta L Cox in bracket VGS minus VT square. Okay, and further if you try to simplify this equation, you will get this equation. Okay, now if this delta L by L is very, very less than 1, this term, we can ignore this term. And now you can rewrite this current equation as 1 by 2 mu WL Cox in VGS minus VT square in 1 plus lambda VDS. Now see, this equation is with consideration of this channel length modulation effect. But if you want to derive only a simple derivation of the IDS, this is the equation. IDS is equal to 1 by 2 mu W by L Cox in bracket VGS minus VT square. Okay, so these are the design equations of MOSFET. Now again, in each region, what are different design equations? So in cutoff region, IDS is 0, so there is no question of equation. So VGS is less than threshold voltage. Okay, and see here we are talking of the N channel E MOSFET, N channel enhancement type MOSFET. Always remember, we are deriving this equation for the N channel E MOSFET. E stands for enhancement type MOSFET. Now for linear region, what is equation? Or first, what is condition to operate MOSFET into a linear region? So VGS minus VT must be greater than VDS, and it is must be greater than 0. It is must be greater than 0, right? So in with this condition, the actually MOSFET operates into a linear region. Okay, now ID, in this case ID is equal to mu W by L Cox in bracket VGS minus VT multiplied by VDS minus 1 by 2 VDS square. Okay, this is the equation for IDS in linear region. Okay, what happens in saturation region? For or first, what is the condition for saturation region? So the condition for saturation region is VGS minus VT is again greater than VDS is much greater than 0. If you further increase positive voltage, your MOSFET will go into a saturation region, right? So what is equation for that? IDS is equal to 1 by 2 mu. Mu is the electron mobility, W by L Cox in bracket VGS minus VT square. So this is the IDS equation in case of saturation region. So these are the different equations, design equations of MOSFET. Okay. Now next part is a second order effects. MOS second order effects. What are these MOS second order effects? So there are different what we can say uh, as in BJT, there is a different effects, right? Temperature effect, body effect. So in case of MOSFET also, there are certain non-linear effects or non-linear effects that we may experience, right? While we are designing something with the help of MOS transistors, we have to consider this non-linear effects, right? That is called as second order effects. So what is first effect in that second order? It's a body effect. Okay. Now, as you see in the right hand side diagram, so which type of MOSFET is this connected in series? It's a NMOS, right? And wherever it's a bubble, it's a PMOS. That is the PMOS, symbol of PMOS. Okay. So these are the N type CMOS connected in the series or MOS connected in the series. So what happens? The MOSFET which is nearer to the positive supply volt, right, which dissipates the highest temperature or which dissipates the highest amount of heat, right? And heat, the amount of heat which it is dissipating keep reducing as you traverse from the positive towards the ground, right? पॉझिटिव्ह टुवर्ड्स द ग्राउंड. म्हणजे एनमॉसच्या केसमध्ये जसं जसं तुम्ही पॉझिटिव्ह सप्लाय पासून ग्राउंड कडे येता, considering the MOS has been connected in series combination, you will experience the highest temperature at the positive terminal side where you have connected it with the VDD or VDS maybe, and there is a least temperature in case of ground case. Exactly opposite is the case. Exactly opposite is the case with the PMOS transistor, right? In case of this PMOS transistor, at the VDD side or positive side, you will experience a less amount of heat dissipation. And as you travel towards the ground, you will get the highest amount of heat dissipation. And this effect is called as body effect. Okay. And basically whatever the threshold voltages that you are applied towards the gate, that is the these actually VT is a function of voltage between source and substrate, right? Source and substrate. Okay. So you can show the you can see the graph of this VT versus this VBS. This VBS means bulk to source voltage, bulk to source voltage, and these are the effect for NMOS and PMOS. Okay. So first one is the body effect. Next is the second order modulation. Next is the second order sorry, channel length modulation. Next second order effect is the channel length modulation. So what is channel length modulation? So channel length is a function of VDS, right? Whatever the channel, this L is nothing but the length of the channel and this is the width of the channel, right? So basically channel length is a function of VDS because from VI characteristics you can come to know, as we increase the VDS, the channel also keeps on increasing and current will also keep on increasing up to pinch off point, right? Up to pinch off point. So basically channel length is a function of VDS. When VDS is increased, the depletion region of the pinch off at drain shorten the channel length. Means what? Now if you keep on increasing the VDS, the one point will come where, right, the pinch off will happen and there is no further increase in the id, right, drain current. There is no further increase in the drain current. That means the depletion region of the pinch off at drain shorten the channel length, and this is called as channel modulation effect. This is also second one of the second order effects that is experienced by the MOS transistor. Okay. Third one is the Fowler Norm tunneling. Fowler Norm tunneling. What is this? What happens because of this effect? When the gate oxide is very thin, right? As you know, from the construction of MOSFET. In case of MOSFET, there is a SiO2 insulated layer of silicon dioxide we are applying. So if that gate oxide layer is very thin, right, then what happens? A current can flow from gate to source by electron tunneling through the gate oxide also, right? Means along with the channel, along with the channel, the electron can flow through that gate oxide layer also. Electron can flow through that gate oxide, that means that insulating layer also of SiO2, right? And that particular effect is known as Fowler Norriam tunneling. Okay. Now next second order effect is a drain punch through. Okay. What is this drain punch through? Now consider if a drain voltage is high enough, the depletion region around the drain may extend to source, right? If this drain voltage, if you increase the VDS as at a max level, then what happens? The depletion region around the drain may extend to source. The depletion region may extend towards the source. Now what happens because of this? Thus, it causing the current to flow irrespective of gate voltage, right? That causes the current to flow irrespective of gate voltage. Means what? Now in this case, if you haven't applied any gate voltage, then also the current will start flowing, a very small amount of current, that may be in a micro ampere or even nano ampere, right? But it will start flowing irrespective of the gate voltage. But when this happens, when you increase a drain voltage VDS beyond certain value, if you increase that voltage beyond certain value, what happens? The depletion region around the drain may extend to source, and it is called as drain punch through. Okay. Now the last two MOS second order effects are, first one is the hot electron effect. Okay. And last is the subthreshold region. Now what is this hot electron effect? When the source drain electric field is too large, right? When this source and drain electric field is too large, the electron speed will high enough to break the electron hole pair, right? Whatever the VDS, right? Drain to source voltage that you are applying, electric field means it is similar to the voltage that you have applied. So if this VDH is too large, the electron speed will be high enough to break the electron hole pair. Moreover, the electron will penetrate the gate oxide, causing the gate current, right? Electron can able to penetrate into a gate oxide region, and that can contribute it into a gate current. Okay. So this is of hot electron. When you can experience this effect, when you apply a tremendous amount of VDS, right? Very large. Probably this effect may happen into a breakdown region of MOSFET, right? Where you further increase the VDS beyond a limit where the device will get breakdown, and because of the hot electron effect, what will happen is the electron speed, because of that electron speed, the very high speed electrons can that able to break that electron hole pair, right? And moreover, the electron will penetrate into a gate oxide, causing the gate current. Okay, this is called as hot electron effect. And the last one is the sub threshold region. Okay, what is this sub threshold region? So the cutoff region is also referred as a subthreshold region. Basically, as you know, at the lower end side of MOS transistor, there is a cutoff region. The in between region, linear one, is the linear region, or in other, it is also referred as a ohmic region. And the upper part of VI characteristics curve is the saturation region. Okay, basically these three basic regions of the MOS transistor. So this subthreshold region, right? Basically, this subthreshold
भारी
region
आहे
is also called as
कळलं
cutoff
हा
transistor.
कळलं इंटरेस्टिंग आहे अजून काय काय भारी भारीच आहे काय म्हणते त्याला काय म्हणते फक्त याला एपीआय एपीआय यू आर
Prathamesh Vattamwar, will you please unmute your mic? Okay, concentrate here. See, subthreshold region is nothing but the cutoff region. Okay, so when the IDS increases exponentially with IDS and VGS, right? So what happens at this particular what we can say a juncture where the IDS start increasing, right? IDS start increasing. It is not a what we can say a very linear increase. It's called it's will increase exponentially, right? Now I hope you are clear with the what is linear line and exponential curve. What is linear curve and exponential curve, right? So at this juncture, right, I have pointed with this blue dot. Okay, at this juncture you can see it is not a linear increase, right? After that, after certain value of IDS, yes, there is a linear rise, but up to that certain value after threshold there is a exponential rise in the IDS, right? IDS increases exponentially as you increase the VGS and VDS. As you increases VGS and VDS, right? So this effect also is a second one of the second order effect of MOS transistor. Okay, now we will quickly revise whatever we have learned in the today's lecture. Okay, first what we have seen the design equations. Okay, again I will repeat it for you. These are the design equations. So first three basic equations we have made assumption, and after substituting first equation into second, you will get this equation of IDS. Again this q1x value we will replace into the equation number uh, uh, 4, I can say, right? Then after you will get this equation. Finally, when you solve this integration, you will get this equation. Thereafter, if you consider for a n MOSFET, right, or that operates into a saturation region, VDS is equal to VGS minus VT. So if you replace that VDS value, you will get this type of equation. If you consider after a channel length modulation phenomena, that is L dash is equal to L minus delta L, you will get this final IDS equation. Okay, now depending upon in which region you are operating a MOSFET, so this cutoff region will have IDS is equal to 0, right? For a linear region, this is the ID equation of IDS. IDS is equal to mu, that is the electron mobility, W by L COX, right? In bracket VGS minus VT into VDS minus 1 by 2 VDS square. Okay, this is for linear region or ohmic region, and this is for the saturation region, right? This is for the saturation region. What is equation of IDS for saturation region? Saturation region IDS is equal to 1 by 2 mu W by L COX in bracket VGS minus VT square. VGS minus VT square. Okay, this is the equation of IDS in saturation region. Thereafter, we have discussed the MOS second order effect, right? First one is the body effect, right? What happens in this body effect? So in case of NMOS, the upper side of the portion of MOSFET which are the closer towards the VDD supply, that means positive supply, that will dissipate the maximum amount of heat. And the as you travel towards the ground, the heat dissipation will decrease. Exactly reverse is the case is with the P MOSFET. In case of P MOSFET, the PMOS, which those who are nearer to the VDD, which dissipates the less amount of heat, and as you travels towards the ground, the heat dissipation will increase. Heat dissipation will increase. So these are the body effect. Now what happens in channel length modulation? In channel length modulation, right, it is a function of VDS, and when VDS increases, depletion region of the pinch off at drain shortens the channel length, right? That pinch off, it is the condition, but reason behind that pinch off condition is the channel length modulation. This is the second order effect. Third way is the Fowler and Noriem tunneling. What happens in this Fowler and Noriem tunneling? When the gate oxide is very thin, current can flow from the gate to source by electron tunneling through the gate oxide, right? This effect is called as Fowler and Noriem tunneling. See, whatever we are discussing now, these all are the non-linear effects of the MOSFET that can be referred as second order effect, right? Then next one is the drain punch through. What happens in this drain punch through? When the drain voltage is high enough, the depletion region around the drain may extend to source, right? And this particular thing causes to flow of current irrespective of the gate voltage, and this effect is called as drain punch through. Now next one is the hot electron effect. Okay, what is this hot electron effect? When the drain source electric field is too large, the electron speed will be high enough to break the electron hole pair, right? Moreover, the electron will penetrate into gate oxide and contributing the gate current. This particular effect is called as hot electron effect, right? Next one is the sub threshold region. Okay, what happens in this sub threshold region? First, where this sub threshold region, right, it is nothing but your cutoff region. Okay, first you have to remember this. Cutoff region is nothing but the sub threshold region. Now what happens in this sub threshold region? As you increase the gate voltage, right, above threshold voltage, thereafter up to a certain value of gate voltage, there is a exponential increase in drain current. There is a exponential increase in drain current with VDS and VGS, and this type of effect is called as, or where this effect happens, is called as sub threshold region, and this is also one of the second order effect of MOSFET, right? So I hope you have clear with this. Today we will stop here. Remaining point we will continue in the next lecture. Okay, if you have any query or doubt, you can ask me right now.
No query, sir.
Okay.